Imagine that you are in an automated warehouse staffed by a group of robots who must move throughout the building, moving boxes, organizing, shipping, and so forth. Furthermore, the robots are all affixed to a network of tracks that guide their motion. Our task is to implement a motion planning algorithm for the robots. While this may initially seem simple, it is actually quite non-trivial because we must simultaneously move all of the robots without allowing them to collide. This problem, surprisingly enough, admits an elegant topological solution. Given a topological space X, we define the configuration space of n points in X to be the set of all arrangements of n points in X such that no two points coincide. We can build this space by taking the product of n copies of X and then removing all of the pairwise diagonals. You might notice that this definition is somewhat reminiscent of our original problem concerning robot motion planning. In fact, we can use configuration spaces to solve this problem. For example, consider a tiny automated warehouse staffed by two robots affixed to a network of tracks that looks like a Y. If we imagine the tracks as a graph and each robot as a point, we can model our problem by building the configuration space of 2 points on the graph that looks like a Y. This configuration space looks like this. Suppose our two robots were here and here on the tracks. That corresponds to this point in our configuration space. As the two robots move around independently on the graph, we can keep track of their motion with a single point in the configuration space. Now let's make the robots swap places. We can plot a path through the configuration space that tells the robots how to swap places without colliding. Configuration spaces allow us to solve motion planning problems by leveraging tools from algebraic topology in order to simplify what initially seems like an intractable problem.